afternoon, and thank you for standing by. I'd like to inform all participants that your lines have been placed on a listen-only mode until the question and answer session of today's call. Today's call is also being recorded. If anyone has any objections, you may disconnect at this time. I would now like to turn the call over to Mr. Greg Hataloma. Thank you. You may begin.
Thank you. Hi, this is Greg Hataloma in the NASA Headquarters Office of Communications. And as many of you know, this week, in a first for NASA, the OSIRIS-REx spacecraft touched the surface of the asteroid Bennu, and it appears that all went very much as planned. And with a couple of days of analysis of the TAG-SAM collection head, the team is preparing to make some decisions about next steps. So here to tell us more are Thomas Zurbuchen, the head of NASA's Science Mission Directorate, and Dante Loretta, the principal investigator of the OREX mission from the University of Arizona. A news release about the discussion we're about to enter is going to be on nasa.gov in the next couple of minutes, so please take a look at that. Right now, I'm just going to turn it over to Thomas to start the story we have to tell. Go for it, Thomas.
Oh, thanks, Greg. Happy to do so. And I want to first thank all of you who are taking time to join us tonight for this update concerning the OSIRIS-REx mission. Of course, I want to also apologize to all of you. I'm sure you're planning something else tonight. I doubt, though, it would have been more exciting than what we're going to talk about here. So there's two things I want to talk about in a framing sense. You, of course, know that at NASA, science never sleeps, and that's certainly in the last few days, not only just for Dante and his team, but also for many of us. The second thing is that, of course, we are committed to full transparency in all of our programs, whether or not you're one of the 80,000 individuals who followed our touch and go maneuver live, or whether you watched it afterwards. We prove that to you every time we do something daring, something mighty, and really in places where we don't yet know how things turn out. Of course, we showed you that amazing movie. We talked about it, and we told you on Wednesday that the TAG maneuver looked successful and that there's 3 steps that need to happen now. The first one is that we're going to look at the sample head and see what happened, right? Did we, in fact, collect something? The second one is that we're going to weigh the sample head and that maneuver that Dante's going to talk about to ensure that we have the 60 grams of sample. And based on that, with my decision there, with looking at all of the data, we're going to stow the head in early November. The decision we said we'll make at the end of October. Well, nature is surprising, and so is the exploration of nature. And I want, in just a couple of minutes, I want Dante Loretta to tell you the story, but let me just tell you the bottom line up front. We did step 1 that we talked about. We looked at the sample head, and first of all, it's full of sample material, much more than 60 grams, and, multiple chains of argument without even weighing it tell us that by far the team exceeded what its goals are. There's even pieces that are discernible in it, and so forth and so forth. But there is so much in there that the diaphragm that was supposed to keep the sample in is stuck open, and we observe some of the sample pieces escaping into space, and therefore now time is of the essence. And no, we won't sleep. We'll move it forward. This is why yesterday late, based on looking at all the data together with a team of core experts and the OSIRIS-REx team, I've made the decision to forego the sample mass measurement and kind of ask the team to prepare immediately, to do the analysis to see whether we're ready for stow. The spacecraft team and the Deep Space Network team are working contingency operations in parallel to ensure that we're indeed ready for that stow decision as early as Monday next week. So that's the bottom line up front. But Dante, why don't you tell us more about details? We look forward to that. Go ahead, Dante.
Thank you, Thomas. It's been another set of exciting days on the OSIRIS-REx project. This is the mission that keeps on surprising us, and certainly that was the case yesterday, as I'll describe what happened. As Thomas indicated, yesterday we executed the activities on the spacecraft as planned, which involved articulating the TAG-SAM robotic arm to place the sampling head in front of the SAMCAM. The SAMCAM is the same camera that documented the contact with the asteroid surface. There is a different lens that we put into place, a diopter that allows us to focus on the sample head when it is at closer range that these images were taken. We moved the head over a range of angles. Just for reference, when the sampling head is in the sampling configuration like we saw from the images on Tuesday, that's 90 degrees. And then as we bring it closer to the plane of view of the SAMCAM, that goes down to 0 degrees. We have released a series of images, I believe, that show some of the most interesting parameters or properties that were observed in the imaging sequence. All of these images were taken at the 5-degree position of the head. We have many other images that show this phenomena occurring. It's an animated GIF that shows 4 images spanning a few seconds in between each snapshot, so you're getting some sense of relative motion in the field of view. And the bottom line is, as Thomas indicated, that we do have abundant visual evidence that there is a substantial mass of Bennu regolith that is inside the TAGSAM collection material. It's a little tough to see from these images because we're using exposures that focus on the particles that are escaping from the TAGSAM head. But on the left interior chamber, you can see part of the mylar flap, which is the check valve that basically is designed to keep regolith inside the collection area. At longer exposure images, we can see that there are, in fact, large particles, some of them almost as big as 3 centimeters in visible long dimension and 2 centimeters in short dimension, right at the size that can fit through that orifice into the TAGSAM collection area. And they appear to be jammed in there, and therefore they're keeping the TAGSAM flap open. We've identified 5 particles that are in that configuration, with that largest one approaching 3 centimeters and the smallest one about at the centimeter scale. So that right away is abundant visual documentation of collected regolith. But I can tell you there was a lot of excitement in the mission support area here in Denver yesterday as these images were coming in, because it's clear that there is a large population of particles that are existing outside the head. And I was immediately concerned because this is loss of sample and sample mass. We have done a lot of analysis on the size distribution of these particles, and you can get a sense of the sizes of them if you're looking at this GIF's animated sequence. You'll notice that there are some black horizontal features that are visible on the base plate and that move with time. Those are long shadows that are being cast by particles that are floating in space just in front of the head. And so you can actually measure the thickness of those shadows. Knowing the position of the sun, you can get particle size estimates very precisely. We are seeing particles in the sub-centimeter range up to about the largest particle of 1.5 centimeters in longest dimension. They're very flaky in structure, which is interesting, similar to what we observed during the TAG event. So we do consider the shape of the particle when calculating the observed mass in these images. We're using a reference density of 1.8 grams per cubic centimeter, and that's been extensively discussed within the science team in the project based on Bennu analog minerals and meteorites and our knowledge of that material. Within any single image, we see between 5 and 10 grams estimated mass floating in space around the TAGSAM head. And for reference, the baseline science requirement for this mission is 60 grams, so a substantial fraction of the required collected mass is seen escaping from TAGSAM. We have done a whole series of analysis to estimate how much mass we think we have. Thomas alluded to some of those measurements. One area that is receiving a lot of intense analysis is in understanding the attitude of the TAGSAM head just prior to the gas bottle firing. We released some images on Wednesday that show right before contact and right after surface contact prior to the gas bottle firing. We did see that the TAGSAM head penetrated some distance into the asteroid surface. We're estimating that distance at around 5 centimeters right now. That is excellent news. In all of our laboratory testing of TAGSAM performance, whenever we push the head down into the compliant regolith, that inner chamber, like we're seeing in the GIFs that we released today, gets preloaded with about 1,000 cubic centimeters of volume, and therefore using that 1,800 or 1.8 grams per cubic centimeter just under those conditions. That is when TAGSAM head is at its highest collection efficiency and in many laboratory tests, that's when we got the full collected head, and that's the 2 kilograms of sample that we've been referring to. We don't have direct confirmation of that large of a mass, but we do have estimates that range into the multiple hundreds of visible mass, and that visible mass is only occupying about 20% of the possible tag SAM volume. So we do have, at 20% of the volume, we're estimating possibly 400 grams of visible material. So that's consistent with a very high collection amount of material. And that is also what we would have expected based on where tag SAM was placed when the gas bottle fired. We've been reconstructing the event in great detail. We know the tag SAM penetrated very deeply into the asteroid surface over the 5 seconds of collection time that we had designed to. Current estimates are anywhere from 24 to maybe as much as 48 centimeters deep into the regolith that the tag SAM head went during that time. So we got very far down into the asteroid surface, and the gas was being expelled throughout that entire time. And quite honestly, we could not have performed a better collection experiment. So with all of that underneath our belt at this point, I am highly confident that tag SAM was successful, that it collected abundant mass, definitely evidence of hundreds of grams of material, and possibly more. My big concern now is that the particles are escaping, because we were almost a victim of our own success here, and some of the largest particles left the mylar flap open. You got to remember the entire system is in microgravity, so it's behaving like a fluid, and we are moving the arm around to get these images, so that's imparting kind of random motion, and particles are kind of diffusing out. They're not moving very fast. We've measured their rates at just under centimeter per second or so in the fields of view here. But nonetheless, it's valuable scientific material. We have abundant evidence of a successful collection event. We are concerned that the sample mass measurement that was planned for tomorrow would impart additional forces and actually cause us to lose mass, and that is going in the opposite direction that we want. So I've been working with Thomas very closely. It's actually been a lot of fun. I think the conversations that we've been having as we parse through all of our information to make these key decisions, and we're in agreement that we have enough evidence of successful sample collection that we don't need the sample mass measurement, and it would risk loss of material, so that is not a prudent path to go down. So we have waved that off. We had a braking maneuver today planned as well, where we're going to stop the motion of the spacecraft relative to Bennu. We are not going to execute that maneuver because that would also impart forces on the sample head. So I've basically directed the team to put as minimal activity on the spacecraft as necessary and start focusing on an early stow of sample to preserve and prevent any future mass loss. We're still working with Thomas and the agency about the timeline on that, but we're hopeful that we can expedite that and begin next week. So I think that's everything that I needed to cover here. It's very exciting, very surprising, but overall excellent news. We had a successful sample collection attempt, almost too successful. Material is escaping, and we're expediting stow as a result of that.
Okay, thank you, Dante. We are ready for questions now. Operator, if you could proceed with the first one.
Thank you. First question comes from Eric Berger with Ars Technica. Your line is now open.
Hi, good evening. Thanks for doing this. Can you, Dante or Thomas, talk about the potential of losing all that you've gotten? You said this behaves like a fluid. You're not trying to put any motion on the spacecraft that would accelerate the loss. But do you have any concern that as you go to sort of stow this sometime next week, it's all going to go out? I mean, what sort of evidence do you have that, like, it's just not all floating away within the next 24 hours? I guess that's the concern I would have. Thanks.
That's a great question, Eric. Thomas, do you want to have anything to answer that, or do you want me to take it?
No, go for it. I'll add if needed. Go ahead.
Okay. Thank you, Eric. We have absolutely thought about that, and that is why I'm moving down a path of minimizing any force on the tag SAM head and moving to stow as quickly as possible so that we don't basically minimize the amount of mass that could escape here. I mentioned the mass estimates between 5 and 10 grams of material that is outside the head that is visible in an individual image. It is moving slowly. Imagine it's kind of like a cloud of particles, but some of it is escaping and new particles are observed leaving the head. So there is also a flux of material that's coming out of there. The conditions under which these images were taken involved a lot of motion of the arm and the head. So we think this is not a steady state mass loss. And in fact, the one area that we look to that can help us with this is devices on the spacecraft called the star trackers. These are cameras that automatically scan the sky looking for point sources against a known star catalog, and the spacecraft uses that knowledge to orient itself in space. But it just gives you also counts on number of point sources detected. We did see an increase in that signal as we were, as a result of moving the arm into the position for these assessments. And then since we've put it back in its parked position, I'm not sure I mentioned that, but TAG-SAM is now back, tucked away on the side of the spacecraft, and that signal has gone down. So we do feel like when we get back to parked position, we minimize motion on the head and minimize mass loss there. One of the key activities for the team is to go through the existing stow sequence, acknowledging that we're in a contingency situation that we didn't expect, and modifying the stow sequence with all of those things under consideration and minimizing the amount of mass loss. And quite honestly, Thomas has been very explicit to me that that is the area that he's still waiting to assess from the team, and we are preparing that intensely today, and we'll be briefing that out this evening and tomorrow morning as well. We do see that there is very little light that's being transmitted through the filter screen on the TAG-SAM head. That's one of the lines of evidence that we're using. We have a series of images we acquired in November of 2018 when the TAG-SAM head was empty. We can compare these images that were taken yesterday. We are looking at about 90 to 95% of the screen is blocked and no light is passing through. And that is giving us confidence that there is a lot of material in here. So estimates are coming in the hundreds of grams. I'm optimistic that it's even higher than that. And that's partially based on the very high opacity of the screen. So we think we're losing a small fraction of material, but it's more than I'm comfortable with. I was pretty concerned when I saw these images coming in, and I think the most prudent course of action is to very safely stow what we have and minimize any future mass loss.
Okay, thanks, Dante. I just wanted to point out for everybody the news release with details about what we're talking about today is live on the nasa.gov website, so you can take a look at that while we're talking or afterwards if you have further questions. We can take our next question, operator.
Next question comes from Lauren Grush with The Verge. Your line is now open.
Hi, thank you so much for taking my question. I'm wondering if I don't know if you said this earlier, but can you tell the rate at which these particles are escaping out into space? And is there no possibility of trying to close the diaphragm before you stow it? Thanks.
We don't have a good quantitative number of the total flux in and out of each scene, mainly because the imaging sequence was varied in time and we didn't expect to be making these kinds of measurements. We do know the particles are moving at the rate of about a centimeter per second or so. And they're in a cloud of particles, so they're not all linearly radiating away from the TAG-SAM head, so they do seem to be kind of a random motion population. The worst case estimate would be that that 5 to 10 grams that we see in the frame is being lost on a regular basis. That's overly conservative, so I think we're on the order of a few grams to 10 grams was probably lost as a result of the activities yesterday, and it's gone way down because we have minimized all motions of the head since this sequence was implemented.
I think I want to only add, Dante, and I think you said it already, but the gap in the diaphragm is highly localized.
Right.
And,
sorry. Yes.
The opacity is around the circle. So if you looked at this entire kind of thing like a clock, right? Say the gap in the diaphragm is at 9 o'clock, and so the opacity and kind of the system is really all the way out over there at 3 o'clock. Is very, very dark. So kind of particles would have, a really long random walk. So it's kind of, to get over to the holes. So needless to say, time is of the essence. What's also important, and I think we're doing it exactly the right way, Dante, between us, is to really make sure that we're really thoughtful and look at data very quantitatively, which is, discussions of the type that we've had in the last 24 hours, can exceed 2 hours at a time, really thinking through this together, making sure that we're really not kidding ourselves in any of these, because we all have one goal, right, Dante, and that is bring the maximum sample back to Earth. And so we do not believe that there's anything we can do with the system that we have to go fix the diaphragm. So really the variables that we can control are, number one, what Dante talked about, which is how much we rattle this thing around. And so we've minimized that with the actions that we took already. The number two is to shorten the time to get this kind of stowed, at which point, of course, the particles are locked into the capsule that will bring them back to Earth.
Okay, thanks. We're ready for the next question.
Next question comes from Neil Greenfield-Boyce with NPR. Your line is now open.
Thanks for taking my question and having this briefing. So I'm trying to understand exactly what this diaphragm type thing that is stuck open. I'm looking at the diagram of the TAGSAM head collection device now, and it looks like when it pushes down, there's a sort of circulation through, and like on each side, there's like little flaps that come up. Is that exactly what you're talking about? I mean, and I'm just trying to visualize this, and if you could explain a little more about how it's sort of propped open, and like, is this a diaphragm that goes all around the cylindrical head, or is it just in a couple of places? And then I guess the other question I have, other than just trying to get a better grip on exactly what's being propped open, is did you ever see anything like this in your simulations, back on Earth? And then the final thing, and I'm sorry to be asking so much, but I'm really interested in this. Why not just stow right now? Like, what are you guys waiting for? Like, if you guys are worried about losing material, it doesn't sound like you would be going for another sampling attempt, right? So why not just stow the thing?
Yeah, thank you, Nell. Those are all great questions. So let's start with your first one. I believe you're referring to the animation that the project has produced, which shows you the gas injecting down into the regolith, circulating, and then up through a couple of flaps, one on the left, one on the right. That is got circular symmetry. So you could, spin that diagram around. And so the flap is like a ring that's around all sides of the center, what we call the deflector cone inside the TAGSAM head. So the gas drives particles to that deflector cone, and then they bounce through that mylar flap and into the collection chamber. Does that help with the geometry?
Yeah, it does. Mm-hmm.
And then when we look at the images that we released today, if you look over at, Thomas mentioned kind of the 9 o'clock position, if the TAGSAM head is a clock face, there's this wavy kind of, there's the crescent, that's the deflection cone. So the deflection cone is like right at the center, it's half illuminated. And then next to that, there's part of the mylar flap that you can see. It's the brighter area, and then it looks like it's right at the 9 o'clock position. It's kind of pushed in towards the center of the TAGSAM head. And in other images, we haven't released those yet, but at longer exposure images, we can actually see that is a large rock that is pushed and wedged in between the outer rim of the TAGSAM and that mylar flap, and that's one of the areas where the flap is being held open. There is no way to articulate that flap. It's a passive component, and whatever configuration it's in, that's what we have to accept. We're not sure the force that's holding the wedging rock in there right now. My guess is it's got to be fairly strong, because it's right at the size limit that could pass through there. So it kind of got jammed in. And we do see in other image analysis that flap is clear, and through careful assessment, we can see stuff on the other side of it. So we know behind that flap, there's a bunch of asteroid regolith as well. And then these big particles were probably coming in late and hitting that flap, and it just had so much material behind it, it couldn't push any farther back. We did not see this occurrence in our test campaign, which we thought was pretty extensive. It did include large rocks. It did include buried head. The thing we didn't test that we saw during the TAG event was this really deep penetration. I mentioned that the TAG SAM itself went possibly as deep as 48 centimeters into the asteroid's surface. So there was a lot of force that was imparted in addition to the gas that provided more mobilization of material. So I really think that we're looking at a substantial mass and just the last stuff that was getting in there, there was simply no room to accommodate it. And as a result, material is leaking out through the small gaps that were created. Remind me if there's part of your question I haven't answered.
Yeah, why not just like call it a day?
Yeah.
You know, like why wait till Monday to make this decision?
Right, and we are going down the path that we are expediting stow as quickly as possible. The one area that we want to spend, the team needs just a little bit of time, is the procedure that's developed and the commands that are on the spacecraft to stow did not consider that material might be coming out of the TAG SAM head. So we want them to go through that procedure. It's a very tactical operation with a lot of ground in the loop decision making. We move the TAG SAM arm, we take images, we downlink the images, we evaluate the position of everything, and then we make the decision to continue, or if we see something we don't like, to back up and rethink our approach. So we want the team to be able to go through the current validation program and say, okay, what do you do differently now that we think that particles might be falling out of TAG SAM, landing on surfaces in the return capsule, making sure that they don't cause mechanical interferences. So that's part of it. The other part of it is we are moving to get DSN time on the Deep Space Network so that we can be in constant communication with the spacecraft, and that takes a little bit of time, and maybe Thomas wants to speak to that aspect of the operational side of the business.
Yeah, I mean, yesterday, after we had this extended meeting that at which, after the end, I really waived this measurement maneuver because of the evidence that's provided. Do you mind, Dante, if we just quickly talk about one piece of evidence? If you look at the picture, you know that very dark thing, that diaphragm is actually transparent before you have sample there, right?
Right.
Right. So I mean, just for you to know, right? There's stuff there, right? So lots of it. Anyway, right after that, I actually talked to the various leaders of the Deep Space Network and basically prioritized this activity. They started yesterday evening to work contingency operation to make sure working that we're ready to actually do this, this maneuver, with all the attention that we can give it. So that of course means that we're making sure that other missions that these antennas are serving as well, that we're doing a planning such that kind of from a portfolio perspective, we achieve two objectives. Number one, we store as fast as we can once the decisions and the analysis are made of the type that Dante talked about, and number two, we do so with minimum negative impact to the portfolio overall. We're of course used to do that, and this team is very well performing in all of our missions. So they're already working with OSIRIS-REx.
Okay, thanks. Next question.
Next question comes from Gina Sunseri with ABC News. Your line is now open.
Is there any thought to going back and taking another try at this, or you just moved past that point?
We have moved past that point. Everything went exceedingly well. The challenge that we have in front of us is due to the fact that the TAG SAM is probably really full of material. So there is no benefit to going back. I think the experiment was so successful on Tuesday. We got TAG SAM exactly into the position and location on the asteroid surface that we wanted it to. The nature of the spacecraft surface interaction was ideal for sample collection. So I am highly confident that it was successful, that we have more than the 60 grams of material that we promised Thomas and the agency that we would deliver. And the most prudent thing, my number one job on the program is to defend and maintain the scientific integrity. And with that perspective, the most important thing is to get this sample safely stowed and minimize any more loss.
have nothing to add. I agree. And we did so, as I said, really looking all the chains of argument that focused on both the calibration measurements, the test measurements that were done before, but also the optical and physical evidence that is provided through this image and other data that Dante and the spacecraft team have.
Okay, next question.
Next question comes from Marcia Dunn with Associated Press. Your line is now open.
Yes, hi. I have several little questions. When is the earliest you will attempt to stow this? Would it be Monday? And if a rock is jamming this open, will this sample head go neatly into to the capsule for return? I mean, will it fit? In other words, if it's jammed open, will you still wait till March to leave Bennu? And lastly, Dr. Loretta, you mentioned early on that the device penetrated 5 centimeters, and then you were talking about 48 centimeters. So could you clarify the difference there? Thank you.
Yeah, let's start with that last question. So we made contact with the asteroid surface. We pushed in 5 centimeters, and then we fired the gas bottle to begin TAGSAM collection. That gas continued to expel for an additional 5 seconds. So total time there is 6 seconds of contact plus collection time. So the first second we penetrated in about 5 centimeters, and then over the next 5 seconds we continued to penetrate deep into the asteroid surface, possibly as deep as that 48 centimeters. At which point the back OA thrusters were engaged in reversing the motion of the spacecraft up and away from the asteroid surface. In terms of the timeline of activities, also kind of relevant to an earlier question, one of the things we have to do before we start to stow is we do need to check out the STOCAM. This is an imaging system on the spacecraft that looks at the sample return capsule. We have released images in the past after launch of the sample return capsule closed. We have seen that there is dust floating on our other optical elements, the navigation camera that was used for natural feature tracking, and the SAMCAM, which used to document the interaction with the asteroid surface. So we do need to know the state of that camera, and the dust floating isn't a problem. It just changes the exposure times. I like to think about, when you're wearing glasses and the glasses are pretty dirty, you don't really notice it until you take the glasses away and look and clean them. But not as much light is passing through those lenses. So you just need to integrate the camera time longer for that activity. So that is one reason, and one thing we plan on doing on Monday is checking out that camera. So we're hoping to begin the stow activities on Tuesday, but we're still going through reviews here internally. As I mentioned, evaluating the sequence and understanding changes to that sequence that deal with the environment that we find ourselves in, that is actively shedding particles from the TAGSAM head, and any changes or additional verification steps we want to add to that sequence to make sure that none of this presents a hazard. In terms of material that could be blocking our stow, we worry about anything that's 5 millimeters or bigger protruding off the base plate. Particularly, we were worried about the contact pads. We do see a couple large particles stuck to the contact pads. The largest one is about 4 millimeters. Again, referring to the TAGSAM as a clock face, the large particle is at around 730 on that contact pad and towards the outer edge of the base plate there. That would be the only one that would present a potential hazard, and it's below our tolerance, so we're not concerned about it. You can see a lot of other particles that are stuck on the base plate and the deflection cone. One of the reasons I chose these images for our public release is because of those shadowings. And you see the shadows moving due to particles that are floating around the TAGSAM head, but you also see shadows that are stationary, and those are things that are stuck to the TAGSAM head and are not moving, at least during this imaging sequence here. So the nominal plan is we begin to stow on Tuesday, and of course there's still some project decisions, but that's what we're working towards. And then no matter what, we actually can't leave the asteroid until March of 2021. But once the TAGSAM head is safely stowed in the return capsule and the return capsule is closed, it's protected and there will be no more mass loss. Materials may still leak out of the head, but it'll just be inside the science canister, and we're prepared to clean all that up once we're back on Earth and disassembling the hardware at NASA's Johnson Space Center.
Just mind if I add, and Dante, as always, just correct me if you feel that there's anything that I'm saying wrong. But the stow time is entirely the timing of the stow is entirely given by the work that needs to happen before it. It's not because of another reason. We basically, Dante's and his team, the entire OSIRIS-REx team, are focused entirely on safely stowing this. There is work that absolutely has to happen before that. And if the team finds a way of doing it faster, we're ready to support. We will stand ready. We're all on our phones. I think we're meeting tomorrow morning again at Dante. And so for me, that's the only pacing item. There's no other thing that I'm aware of. Dante, anything you wanted to add? Or?
That's correct. We told the team that this was a priority, but we wanted to make sure we were doing it systematically and thoroughly and carefully, like we do all of our operations here. And the team came back and said they would like to begin this operation on Tuesday, and we're working hard to make that happen.
Okay, thanks. Next question.
Next question comes from Jeff Faust with Space News. Your line is now open.
Yeah, question for Dante. You mentioned that you didn't do the braking maneuver that you had planned in order not to disturb any more material coming out. What's the plan then for basically spacecraft operations over the next several days? You're going to continue drifting away, and then at what point do you do that braking burn and hang around in the vicinity of the asteroid until you depart for Earth in March? Thanks.
Yeah, so we are still moving away from Bennu at the roughly 40 centimeter per second velocity that was imparted by the backaway burn, and currently there is no plan to arrest that motion. So we were only going to do that in the event that we thought a second tag attempt was necessary, and we would start setting up the return to orbit sequence, which is a fairly involved set of spacecraft operations to do that. We had planned on doing that braking burn because we thought in the nominal decision line that we laid out, we'd be implementing a sample mass measurement tomorrow, and we'd be going through a more leisurely decision-making process with the stow activities expected to start in early November. But with this observed mass loss and the priority on maintaining the science as much as possible, we're expediting that timeline, but therefore making the decision that we will be not be returning to the asteroid. So we said our goodbye, I believe, to Bennu on Tuesday, and we're solely focused on stowing the sample safely, and then once that's done, on preparing for return cruise and Earth return.
Okay, next question.
Next question comes from Chris Davenport with Washington Post. Your line is now open.
Thanks, guys, for doing this. Two quick ones. Are you able to keep the camera on the TAGSAM head sort of 24/7 so you have constant eyes on it and tell if there's more spilling? And then second, once it's stowed, is there any way to measure how much sample material you have, or was the only way to do that when you stick the arm out and spin it around and measure the moment of inertia? Or I'm just wondering if you're going to have to wait till it gets home to know precisely how much you have. Thanks.
I think we're going to have to wait till we get home to know precisely how much we have, and that, as you can imagine, that's hard. We were looking forward to a sample mass measurement, and then the certainty that gave us in terms of planning out the sample analysis activities. But the good news is we see a lot of material, so we are in the positive situation of having, we believe, a lot more than the 60 grams that we were required here. So we don't believe there is a way to measure the mass once we're inside the sample return capsule. We certainly have not gone through any kind of design or verification process for that kind of measurement. The sample mass measurement was really it. Your earlier question was about the camera. So the images that we released today, we had to articulate the TAGSAM arm into a very specific position that we are not comfortable maintaining over the long period of time. We prefer the TAGSAM head to be in what we call the parked position, which was similar to its launch configuration. It's tucked away on the side of the spacecraft. It's in shadow, so it stays nice and cool. We do have to place it in the sun to get these kinds of images, and we had a very deliberate timeline to minimize exposure to the sun to prevent the head from getting too warm and therefore possibly compromising the sample. So we believe the safest place for the TAG SAM to be parked is at the side of the spacecraft, but we don't have a camera system that allows us to monitor that. We will be using both the SAM-CAM and the STOW-CAM to monitor the TAG SAM head status throughout the entire STOW sequence, but not currently in the field of view of either one of those imagers.
Okay, next question. Hello, we're ready for the next question.
Next question comes from Greg Avery with Denver Business Journal. Your line is now open.
Yes, thanks for taking our question. I'm curious, is the stowing program that OSIRIS-REx went up with, is that the program that you'll eventually use? Is there any modification to how it'll be stowed that you guys will make because of the collection arm being jammed open?
Sure. So just to be clear, the collection arm is not jammed. It's the head and the mylar flap. The arm is fully functional in terms of the wrist, right, the elbow, and the shoulder motor, and there's no sign of any mechanical damage to any of the arm components. So the arm seems to be in great shape. It's the head that has this mylar flap that's jammed open that's causing sample loss. So we're confident in our ability to articulate the sampling head into the proper stow configuration. Your question is a great one. That's exactly what the team is discussing today. As you can imagine, the operations team is working through all of the details that are needed here. I have heard some things, but I'm still waiting for a report that's going to come out of that. We will be changing some of the order of operations to minimize disturbances to the head throughout the stow procedure, and also to, in the event that an anomaly occurs with SRC operations, making sure the TAG SAM is protected and it's best done in the park position. So I think we're looking at maintaining in the park position for as long as possible until we understand everything else about the system is ready to go, and then begin the stow operations. But that's work in progress right now. I know Thomas, that's part of his direction to me, is to make sure the team has thought through that very carefully in this contingency situation and come forward with very explicit modifications to the existing procedure that deal with the contingency that we're in, and we expect to be sending that report out this evening.
Nothing to add.
Thanks. Next question.
Next question comes from Keith Culling with NASAWatch.com. Your line is now open.
Thanks. Question. You're doing all of this in microgravity, so you've got a lot of sample things are pinging around. I'm looking at the diagram that shows the sample head, and it looks like there's some space around it inside the return capsule. So the question is, if you've got stuff bouncing around and you're having issues with closure and so forth, if you get material outside of the sample container but inside the reentry vehicle, is that contamination? Can you do science with that? I assume you were expecting some of that. And second question, if you have an issue with closure and so forth, how hard can you close this reentry capsule, and do you only get to close it once, or can you hammer it down a couple times if you think it needs to get a better latch?
Thank you, Keith. Those are some great questions. We certainly do expect that material may move around and actually exit TAG SAM once it's inside what we call the science canister inside the return capsule. So that's a separate compartment that holds the TAG SAM, and it separates it from the avionics and the parachute and some other components like that. So there is a science canister, and we expect probably material is going to be all over the place because the Earth entry, the parachute deployment, and the ground impact will each impart shock events during the reentry sequence, and that may move material around and it may fragment material. I won't get into the details of the sample return capsule strength because that is a Lockheed Martin design, and I just don't have those numbers at the top of my fingertips right now. I do know that we expect it to be a one-way ticket. That is, certainly once you've placed the TAG SAM head in the capture ring, you have to fire a tube cutter, which cuts the plumbing from the TAG SAM gas bottles down to the head, and then a separation bolt. So that is a one-way ticket. And then we move the arm away, and the entire head remains inside that capture ring mechanism. And then we'll pull the SRC down There's several latches. Only one latch is required for earth entry, and I know it's very strong, and it'll pull the whole thing, and if there is an obstruction, we're confident that it can overcome that. But I don't have the strength numbers that you were asking for readily available, but we can get those by talking to our design engineers here at Lockheed Martin.
Just to be explicit, all the particles that would exit the the sample head here and rattle around are science, so they're not contamination, right, Dante?
Absolutely. Yep.
Okay, next question. Next question. Hello, we need the next question. You ready for the next question? Hold on, please.
Sure.
I think we're having a technical difficulty. Stand by. Hello, we're ready for the question from space.com.
Hello, hi. This is Mike Wall. Can you guys hear me?
I can hear you. This is Dante.
Okay.
Thank you.
Okay, great. Thanks a lot. Just a quick question about STOW. Is it just like once you guys send up the commands, it'll just execute, or are there little stop points in there where you can see if there's something abnormal, if maybe there's a particle stuck on the plate that's a little too big, you can halt things? Or is, as you're saying, it's just like a one-time go and you just have to hope that everything's all right and it just goes? Thank you.
Sure. Yeah, the STOW procedure will be a very deliberate, slow kind of tactical operation with many points of downlinking images and then, analysis on the ground and ground in the loop verification and approval to proceed to the next step. So very different than TAG. TAG was a pre-programmed sequence that ran for, over 4.5 hours on the spacecraft with no ground intervention. During these operations, the spacecraft will be at a position we call Earth Point, which means its high gain antenna is connected to the deep space network, and we get a very high data rate. And we are expecting, full 24/7 coverage during those activities. So we can command the arm to move, command the SNOCAM to acquire an image, downlink that image, analyze it, and then make a decision exactly as you were saying. Did we see a particle that looks like a mechanical interference? And then what do we want to do to mitigate that as we move forward? So it'll be very slow and deliberate and play out over several days of activity.
Great, thank you.
That's why it's so important to have these DSM antennas ready, right, Dante? And that's why the team is working on that already.
That's right.
It's absolutely critical that we get these pictures down with the highest, bandwidth that we can, get it down to the ground for the team to really make decisions on. And of course, the only thing we can't trick is the speed of light, right? It still takes 18 plus minutes going one way. And therefore, for a command, 18 minutes times 2 for a handshake type of thing. So yes, very different operation in this case than the entire attack, which was much more autonomous, right?
Right.
Okay, we're ready for our next question.
Next question comes from Irene Klotz with Aviation Week. Your line is now open.
Thanks. Dante, does it tell you anything new about Bennu that TAGSAM was able to sink so deeply into the surface?
A great question. Yes. We have, as you can imagine, run a wide range of simulations over the years with TAGSAM interacting with the surface of the asteroid. And I remember early on in development, it was a real question. The mechanical properties of the surface of the asteroid were probably the largest unknown in the mission design. And so we had to design everything from a completely rigid surface, like running into a slab of concrete, down to what we called the fairy castle structure with almost no resistance. And that was part of the challenge of the mission, was in coming up with a design that would operate under all of those different circumstances, maintaining spacecraft safety primarily. We're definitely on the much softer end of that spectrum. We are seeing that the regolith behaved very much like a granular medium, and it flowed away from the TAGSAM head as we pushed through. And the science team is absolutely ecstatic about the data set that we had collected. It's too early for me to obviously give science results. My focus has been very much on the operational decisions and maintaining the safety of the sample, but we have a very talented and broadly distributed science team, and people are already working on that. And I touched base with a couple of the team members earlier today just to understand where they were. So we will come forward over the next months as we process the data with some really exciting news. I can tell you the whole interaction was very favorable in terms of getting information that probed the nature of the surface. So we made contact. The contact was sensed by the accelerometers on board the spacecraft. We had over a second of accelerometer data that reflected the force being imparted on the spacecraft from the asteroid's surface. The pogo spring, if you recall the design of the TAGSAM arm, on the forearm there's a spring that takes about 70 newtons of force to compress. That spring did not deflect noticeably at all. So all of the force of the downward force of the spacecraft was complied with by the asteroid's surface, and we're able to keep moving over the entire sequence. By the time the backaway thrusters fired, about 6 seconds after contact, we were still moving forward at 4 centimeter per second velocity. So we were still pushing down through the regolith, and that's where that 48 centimeter maximum penetration depth comes from. That stayed and propagating that 4 centimeters forward. I believe we continued forward motion for another 3 seconds. So it took the thrusters an additional 3 seconds to stop that forward motion and then begin accelerating us backwards, ultimately achieving that 40 centimeter per second escape velocity. And so that's a wealth of information that will provide an enormous amount about the material properties of regolith at the contact point.
Thanks.
Okay, next question. Thank you.
Next question comes from Joey Roulette with Reuters. Your line is now open.
Hey, thanks. Dante, do you know how wide the door is wedged open? Sorry if you mentioned that before, but I was just wondering if there's any sense of the size of the rock that's leaving it open, or how big the gap is that's allowing material to spill out. Thanks.
Yeah, we see the gap is as large as over a centimeter across, and we've actually seen particles that kind of peek over the lip and then slip over the side. It's interesting, and you can really see it in the animation or the image sequence that we released here, that the particles are generally very flaky. They're very thin, and that seems to be maybe a selection effect, that it's the thin, flaky ones that are capable of escaping. We're not sure, but we're not seeing a lot of really rounded or equal, spherical particles flipping out of there. But particles as large as 1.5 centimeters in long dimension are observed, but that they're slipping over a smaller gap because of this difference in their aspect ratios and their flake-like morphology. But we can definitely see that. We have other images in the same attitude that we released today, just at longer exposure times, that get some nice detail on where that mylar flap is depressed. And I think it's the one area, like we've been referring to, the 9 o'clock region in that gap, that rock is in that dimension about 2 centimeters across. which is just about the size of that orifice. And then you can really see in the images we released the profile of the mylar flap. And then where that rock leaves, that biggest gap there is about half the width, or about that 1 centimeter distance that I'm referring to.
Okay, next question, please.
Next question comes from Mark Zastro with Astromag. Your line is now open.
Another question about the stow procedure. But you had mentioned that you had lost a few to 10 grams of material during the imaging procedure, partly just due to the motion of the arm that was necessary for that. So I'm just wondering if you have an estimate for how much you might lose during the stow procedure. Just, I mean, obviously you're going to try to minimize that, but based on the range of motion that's necessary to carry out that procedure, how does that compare to the imaging procedure? Is it comparable, or perhaps more or less?
That is a great question. I can't answer that right now because I don't have the details of the stow sequence, and especially any modifications to the stow sequence that the team is operating here. It will be longer in time, that's certain, mostly because of these verification steps that I talked about, where the ground's in the loop. Thomas mentioned the round-trip light time. So we are expecting probably 3 days of activities versus just a couple of hours of activities that were required for the imaging campaign. And as we go through and evaluate that, we are minimizing the amount of motion. I would expect to see a comparable amount of mass loss, and we'll be documenting that to the best of our ability with the imaging systems. And I don't see a way out of that right now. I think we have to accept that and just redesign and optimize the sequence to minimize it. It's tricky to get the mass flux with the image. The images have only been on the ground for about 24 hours, and there's team members working on that. So because it's a persistent population that's going through a lot of random motion, it's not obvious what the refresh rate is, even over our imaging sequence, and we're trying to figure that out. The best we can do right now is kind of total up the mass that's observed in each frame and use that as worst-case estimates. I expect we'll be losing grams to tens of grams as a result of stow.
Okay, thanks very much.
Okay, we are getting to the top of the hour. We have time for one more question.
Next question comes from Mark Gotch with historicalaerospacenews.com. Your line is now open.
Yes, congratulations, Dante. Your crew and yourself have put together an absolutely amazing mission. To think of 1 meter accuracy at your Nightingale sampling site is just beyond belief. What an accomplishment. Can you tell me, now that you're in this backed away mode from Bennu with your very ample sample, could you tell me how long will you remain in that orbit, and how long will it be before you decide on this mission to break away from that orbit, sending this sample back to our planet Earth? And what will be the total elapsed time that it will take for that sample to return to us on our planet Earth?
Sure. Thank you for that question. So right now we're focused on stow activities. If everything goes according to the plan that's being formulated here, that should be complete within a week from today. We will continue moving away from Bennu at the 40 centimeters per second, and we do not expect that we'll be returning to the asteroid. So we're not in orbit around Bennu right now. We're moving away at a pretty rapid rate. We're tens of kilometers away at this point, and we're in orbit around the sun. With the departure, which is somewhat confusing of a term, but leaving the vicinity of Bennu and getting us on the return trajectory requires a large maneuver on the main engines, requiring hundreds of kilograms of fuel versus the grams of fuel that were used for the tag operation on Tuesday, for example. And in order to optimize that, we have to wait for the position of Bennu and the position of Earth relative to one another to be appropriate based on celestial mechanics. With the fuel that we have on board and the return trajectory that's been analyzed, we can't leave any earlier than the beginning of March of 2021. So we will just be preparing for that return over the next couple of months. When we fire those main engines, it's a single large propulsive event. And as I mentioned, what's been analyzed is a departure in early March, and we're probably going to continue with that because we understand it very well. It's a 2.5-year ballistic trajectory through the solar system, targeting an Earth entry on September 24th, 2023. We will do some orbital refinement as we're approaching the Earth just to make sure we're coming in right through our entry corridor. But for the most part, it's going to be a pretty quiet return cruise for 2.5 years from departure in March of 2021 to Earth return in September of 2023.
Okay, thanks for that, Dante. We are going to wrap up now. As I indicated earlier, there is more detail about what we've been discussing here at nasa.gov, along with the image that Dante was showing in the stream at nasa.gov/live. If you want to hear a replay of this, it will be up for a month. Let me give you that number at 866-373-4996. Again, that's the replay number of this telecon. It will be available for 1 month at 866-373-4996. I want to thank Thomas and Dante for their time and congratulate the entire OSIRIS-REx team, and look forward for more updates in the coming days. Thank you.
Thank you, everybody.
This does conclude today's conference. You may disconnect at this time. Speakers, please stand by.